Hi, good morning or good afternoon, everyone. So my name is Liang Kao. I'm a near Lehigh research scientist. Today, I'm gonna talk about test design and planning using the NHERI infrastructures. Basically, I'm gonna focus on the hybrid simulation framework. So in our near Lehigh facilities, our focus is on large-scale multi-directional real-time hybrid simulations. Well, that's not all only things we do, but here it's just talk about, today I'm just talk about our focus on the real-time hybrid simulations. So real-time hybrid simulations is combining the physical elements with computer-based simulations to evaluate the performance of large-scale components and systems. So if you look at the hybrid simulation papers, they look not really difficult. However, but when you try to do the hybrid simulations, the procedure is a little bit overwhelming. So that's why our near Lehigh facilities can provide you user-friendly tools that enable you as a researchers to readily utilize the advanced technologies and the algorithms we developed to perform the complex experiments, especially on real-time hybrid simulations. So in our facilities, we are enables the researchers to readily perform 3D real-time hybrid simulations of large, complex nonlinear systems subject to multi-natural hazards. We are not only doing the linear systems, especially we do 3D nonlinear systems. And for the multi-natural hazards, typically we refers to wind, earthquake, and we could do other type of excitations too. So and also we do the 3D multi-hazard real-time hybrid simulation systems equipped with numerous response modification devices, for example, as a energy dissipation device like viscous dampers, which can be used in the 3D real-time hybrid simulations. Because the limited space, sometimes you want to have dozens of energy dissipation device, but you can only have like one or two physical device. So we also have the abilities where you can, using the limited physical device and numerically model those devices in the analytical model and using model updatings based on the dynamic behaviors in the lab. The third, we can produce accurate large-scale 3D multi-directional experience. So this could be quasi-static, hybrid, or real-time simulations. Those experiments can involve the nonlinear kinematics of actuators and the specimen's motions. For example, some of the large dynamic tests where your control node of your test specimens or the point when you try to impose your displacements may not be the same as actuators' motions, then these things will involve a lot of the nonlinear kinematics. So in Lehigh facilities, we're able to perform that type of test too. So to do that, we also need to have a precisely hydraulic actuator control, so which is also compensate the amplitude and the hydraulic delay. For our broader impact, so the key questions in natural hazard mitigations can be addressed through research performed in near Lehigh facilities that will lead to development and implementations into practice, new natural hazard mitigation strategies, and innovative resilience structural systems. So like research you performed in our lab will transfer to practice. That's one of our ultimate goal. We also enhance the understanding of response to multi-hazards by accounting for soil structure interactions and the potentially fluid structure interaction effect. We actually could do both. And also, we can give you a comprehensive of system level effects on structure and non-structure components through large-scale 3D system experiments. We're not talking about a single isolated system. We are talking about the entire 3D systems. In here, you can obtain high-quality experimental data leading to improved computation models. So because we are doing real-time hybrid simulations, you are not going to do a pure numerical simulations. All the test experiment data will help you to improve your computation model. And the most important things, we are training the next generation's workforce. So which means the students, they were trainings in our lab, they doing tests in our lab, could be the leaders for in the futures on the natural hazard engineering. So let's talk about the overall concept of real-time hybrid simulations. So typically, real-time hybrid simulations have three components. You see the left component is the analytical substructures, which some things you can confidently to models in the computers. And the right one is the experimental substructures, which their dynamic could be complex or their dynamic could be sensitive to the excitations or the impulse displacements. We can physically model it in the lab. And we need a simulation coordinators which integrates the equations of motions. This is an example on high-rise buildings equipped with nonlinear viscous dampers. So you see this is 40-story buildings subject to the wind hazards. So those wind hazards we can obtain by doing wind tunnel test on FIU facilities, where we can obtain the wind pressure data, and we convert to with a predefined wind load to use on the hybrid simulations. And by combining the analytical substructures, we're giving command displacement to both analytical substructures and experimental substructures. And then we obtain the restore force. So R sub A is the restore force from the analytical substructures, and R sub E is the restore force from the for the physical models in the lab, which typically obtains by load cells. So we're combining those restoring force with the initial force and the structure damping force. And also the F is the wind force we obtain from the wind tunnel test. Then we're able to using the simulation coordinators to calculate the real-time structural response. This is the general concept of the real-time hybrid simulations. Well, if you can, we can also slow down the simulations. As long as your experimental substructures is not rate dependent, we could do slow hybrid simulations. It's totally depending on your experimental substructures. So why real-time hybrid simulations? First, the real-time hybrid simulations enables to do cost-effective large-scale dynamic test, which we're talking about is the real-time hybrid simulations RTHS has lower economic cost comparing to a full-scale shaking table test. And by using a single experimental substructures, for example, single damper, you can use this substructures in a various analytical substructures. For example, you can install the same viscous damper in a full high-rise building, low-rise building, on bridges, and to conduct different type of simulations, earthquake, wind, and it meets the need of natural hazard engineering communities. Also, why we are doing real-time. So real-time hybrid simulations can account for rate dependencies of physical specimens. What we call rate-dependent substructures, such as friction dampers, basal isolators, two mass dampers, which can be investigated using real-time hybrid simulations. But because they are rate-dependent, they are not possible to do with conventional slow hybrid simulations because their dynamic behaviors related with the velocity. So real-time hybrid simulations, as I talked before, the real-time hybrid simulation consists of general three components: simulation coordinators, analytical substructures, experimental substructures. Each of the components has its own implementation issues and challenges. For simulation coordinators, first is the challenges in the numerical integration algorithms. We want the numerical integration algorithm be accurate because so every simulation is approximate analysis. We try to minimize the error as slow as possible. And in Lehigh, we prefer to do explicit integration scheme. So typically, the integration scheme you can count as characterize as implicit and explicit scheme. So what explicit schemes means the next step of response, for example, displacement, will only depending on the combination of current step and the previous step. This and the implicit is also depends on the next step. So the reason we prefer explicit scheme because the implicit scheme requires iterations. Sometimes if you cannot converge in each time step, you are not able to produce accurate response. You cannot even do the hybrid simulations. But however, the explicit scheme, some of the explicit scheme is conditional stables. So which just means if you're using, it depends on the system. If you're using larger time step in a like higher large degree of persistence, your system may become unstable. So that's why we also perform this explicit scheme become unconditional stable. And the third part, we want the integration scheme has the numerical energy dissipation abilities. We try to damp out any undesired participate of higher modes. This things can generate by the noise or something is not realistic. We try to have controllable the numerical dampings energy dissipations abilities. So also for the simulation coordinators, we need have fast communications between the analytical substructure and the experimental substructures, which is Tom is already providing the information on our IT equipment before. And for the analytical substructures, which means what your numerical models in your computers, there's some challenge too. So we want the analytical substructures to able to have a fast and accurate state determination procedures, because you can do as fast as possible and accurate as possible. Then we can modeling the more complex and nonlinear structures. And for the experimental substructures, there are some three challenges. First, we prefer to do large scale because scale matters, right? The benefits of the hybrid simulations is because you cannot like to do a full scale of like high-rise building in your lab. So that's why we only model the portion of the structures in the lab. So the benefits of hybrid simulation is we try to do the large scale, full scale as possible. So to do so, you need to have a large capacity hydraulic systems and the dynamic actuators. Second is sometimes when the control node of your experimental specimens or the imposed displacement locations is not the same as the actuators motions, then there's some like nonlinear kinematic relationship between them. So you need compensators to compensate the actuators motions. And the third one is you have to have a robust control of dynamic actuators to minimize the delay and amplitude errors. So in here, we developed some great solutions to address the challenges. First is for the integration scheme. We developed the unconditionally stable explicit integration algorithms. You can see these three different, you can find those schemes in these three different applications. So for the most recent one, we are using, we call it MKR alpha integration algorithms. So basically they have three equations. The first two equations is a velocity and displacement update. You can see it's pure explicit, which means the future step n+1 is only depending on the current step. And in here, we are introduced three model-based integration parameters, alpha 1, 2, 3. And we are adding these weighted equations of motions to introduce a controllable numerical dampings, which will be determined by one parameter called rho infinity. And also those alpha 1, 2, 3 values can be also determined by the rho infinities. So what does the rho infinity work? So if you take a look on the right graph, so the x-axis is the frequency, the y-axis is the equilibrium damping system. When the rho infinity number equal to 1, so that means there's a 0 numerical dampings we added to the systems. When the rho infinity equal to 0, on the lower mode is close to 0 dampings. But as long as you go for higher frequencies, your numerical damping can be reached to 100%, nearly 100%. So then by adjusting the rho infinity value, you can easily tune the numerical damping system as you need. And also, what we call this integration scheme is one parameter scheme, because all these alpha numbers are determined by the rho infinity numbers. So before you do the test, as long as you give the user-defined rho infinity numbers, the alpha numbers is already being calculated automatically. The second solution is for the analytical substructures. We developed a new explicit force-based nonlinear fiber element for your numerically model your structures. So typically, there are two different types of fiber elements. One is called displacement-based fiber element. The second is called force-based fiber element. The benefit of displacement fiber element is their state determination procedure is straightforward. However, the fiber elements is related with the shape functions. Their curvatures varies linearly, which just means like to model in nonlinear behaviors for a single structure components, you may need to create a numericist elements, which can significantly increase the degree of freedoms in your numerical structures, which will jeopardize the hybrid simulation procedures. We try to have a lower degree of freedoms as possible. That's why we choose force-based fiber elements. The benefit of the force-based fiber element is the nonlinear behaviors of each single structure components can be modeled only using one single element. So it can significantly reduce the structure element numbers and degree of freedoms and numbers. However, the drawback is it requires iterations at the element levels. So that's why we develop our own explicit force-based nonlinear fiber element. First, it's explicit. So it's the same as the integration scheme. So it has to be explicit. Second is force-based elements, which we can significantly reduce the element numbers. The most advantage we developed is we fix the iteration numbers and we carry over the the correction of unbalances force to the next step. Then the iterations will not become a problem for the real-time hybrid simulations. So here's videos as examples. So this is a 3D real-time hybrid simulations of a 2-story reinforced concrete buildings subject to MCE level earthquake. We installed one viscous dampers in the middle base on the 2nd story. And the left graph was the roof displacements and ground accelerations in X and Z directions. And the right upper graph is the damping force and the deformations we obtained from the lab, which also representing the energy dissipations. And the right bottom graph was the moment curvatures from the 1st story columns on the corner. First, you can see from the damping energy dissipations, the viscous damper dissipates a lot of energies under earthquake. And third, if you look at the moment curvature, you see the 1st story column have a highly nonlinear behaviors. Let's highlight the importance is why we're using nonlinear elements. We have to model the structure as a nonlinear element to capture the key features of the structure behaviors. Second, the third one is we develop abilities to do the real-time nonlinear model updatings. For examples, like for high-rise buildings, you may want to install, to retrofit the buildings, you may want to install like dozens of nonlinear dampers. But however, due to the lab space, you can only have a like single or two physical elements, physical dampers in the lab. So what we can do, we can using the limited physical dampers and numerically model those dampers in the analytical substructures. And based on their response in the physical physical dampers in the lab, we can do the real-time online model updatings for the numerical damping systems, which can predict more precisely structural vibrations, which I'm going to show you an example later. The first, we developed a 3D kinematic compensation actuator control algorithms. As I talked before, sometime with a large-scale experimental test, your controlled node on the experimental specimens may not be the actuator motions. For example, in this 3D multi-directional nodes of CLT shear wall flow diaphragm, when you do dynamic testings, your actuator's locations is not the control node where you want the impulse displacement locates. So there's some like nonlinear kinematic relationship between the actuator's motions and the control nodes. Therefore, to compensate the nonlinearities, we developed this 3D kinematic compensation algorithms. And you can find this algorithm in these two publications. The fifth one is for the hydraulic actuators. We know we always have a delay from the hydraulic and or the amplitude errors based on the if you have nonlinear behaviors on your test specimens, like the materials can generate some amplitude errors. You want to develop a adaptive servo hydraulic control for these delay compensations. So if you see these equations, the U is actually the impulse actuator's displacements, and the X is the targeted displacement. So basically, this compensations is following the Taylor series. We have three parameters. The first A0 is related with the amplitude error, and the ratios between the A0 and the A1 is related with the delay. You can find these delay compensations in these publications in EESD. So to summarize the advantage in Lehigh facilities, we're able to do the 3D large-scale multi-directional real-time simulations by using the unconditionally stable explicit integration algorithms. And for the analytical substructures, we developed explicit force-based nonlinear fiber elements, which can be used to model the nonlinear large-scale structures. And we can do nonlinear model updatings. And we have a 3D kinematic compensations and adaptive servo hydraulic control. So here I would like to show you examples on 3D multi-hazardous real-time simulations of our tall buildings. So this is the 40-story buildings. We're also including 4-story basements buildings in Los Angeles. So they consist of a BRB frame in east-west directions. So in the east-west direction, the BRB frame was equipped with outrigger columns. And also in the middle, we have a BRB frame too. So in here, for the multi-hazards, we're considering earthquake and wind. The earthquake, we using MC levels, bidirectional earthquake. And for the wind load, we are obtaining this wind force from the FIU facilities. So those aerodynamic wind tests we did a couple years ago, which is our Lehigh and FIU joint development, which belongs to the phase 1. We got to talk later. So in here, we build a rigid model for these buildings, and we put a pressure test in there, and we obtain the wind pressures. And for us, we convert this wind pressure to wind force as a predefined time history wind force to the buildings. We use explicit MKR alpha integration algorithms, force-based fiber elements, ATS control for actuators, online model updating. I'm gonna talk about this in next slides. So the difference between the wind and earthquake is the low infinity number, because we know we can foresee under the earthquake, the buildings will produce nonlinear behavior. So we want to have a higher numerical dampings than the wind. And both of the real-time hybridization 10 step we use is a 6/1024. So here are some key features of analytical substructures. We have 1,317 nodes and also nearly 3,000 elements, and which consists of 2,411 nonlinear four-space fiber element, 552 nonlinear truss element, and also we have 11 nonlinear explicit Maxwell elements for the nonlinear viscous damper. So in here, what we do is we install the total of 12 nonlinear viscous dampers in the outrigger columns. So 6 in the east side, 6 in the west side. And since we only have one physical nonlinear viscous damper in the lab, which we assume it is installed on the 40-story outrigger columns, the rest 11 nonlinear viscous damper we are numerically modeled in the analytical substructures using explicit Maxwell elements. And to do the real-time model updatings, we're using uncentered Kalman filters to numerically update the dynamic parameters in the numerical damping. And also because for the nonlinear viscous damper, we have to model this as explicit. So everywhere everything is explicit. So the loop is slightly different than I talked about the overall concept. So in the overall concept, you have analytical substructures, experimental substructures, and the simulation coordinators. So instead of feeding back the restoring force from the experimental substructures and the analytical substructures, we also using the command displacements to the experimental substructures and the restoring force to updating the numerical dampers. And after that, we calculate the restoring force from the updated numerical dampers in each time step and combining them as an analytical restoring force to the simulation coordinators, and then calculate the real-time structural response. So this is the videos of the 3D hybrid simulations, real-time hybrid simulations under the MCE level earthquake. So the top one is the roof displacements, and the middle is the BRB frame in the first story on north-south direction, east-west directions. The bottom one is the damper deformations, force deformations representing the energy dissipations. And the right one are the displacement of the roof and accelerations on the roof. So one thing I want to mention is if you take a look at the first story BRB frame, you can see the highly nonlinear behaviors. So even for high-rise buildings under earthquake, the structure will behave as nonlinear. We'll have like highly nonlinear behaviors. And also when you see the structure vibrations, you see the higher mode was dominated. That's highlight the importance is why we have to model this as nonlinear structures. The next one is the under the wing force, which is obtained from the FIU facilities. So because it's in real time, it's about like 10 minutes. We speed up the video so you don't have to watch for 10 minutes. So there's no sounds on the background. So since there's no sound, I can talk during the videos. You can see on the BRB frame under the wing, it behaves pure linearly. And if you see the roof displacements, right? So the wind is actually blowing in the east-west directions. So, but you see the large these vibrations on the north-south directions. This is generated by the vortex sheddings. That's also gonna tell you why we have to model as a 3Ds. So if you only doing 2D models, when the wind blowing in one direction, you're not able to capture the behaviors under vortex shedding. So here's a quick summary. So by adding the damping systems, we are reducing the 30% reductions in the north-south BRB frames. And there's very minimal reduction in east-west because the outrigger frame is in the north-south directions. And under wind load, we're able to have a nearly 50% reductions on the acceleration in north-south directions. On the peak acceleration, we have 35 reductions. So the next, I got a quick wrap up on our recent development. This is one of the students developed a real-time hybrid simulations of structured soil foundation systems, which is focused on the same 40-story buildings where the soil foundation system, we are using a new the neural network models to model the soil foundations. And this project has 4 phases. The first one, phase 1, is also focused on wind loadings, which is we are going to the wind forces obtained from the FIU facilities, and here for phase 1, because the first time we go for the numerical neural network, we're starting at 2D models, and eventually we gotta jump to the 3D model too. So first, we try to validate our 2D high-rise buildings and the neural network models. So we also create OpenSys models to validate our results. So you can see in the OpenSys models, you have 4,000 nodes, nearly 9,000 degree freedom system, and 4,000 elements. But using the neural network, you can significantly reduce these nodes and the degree of freedoms, which means why we're reducing this degree of freedoms, we want to have the ability to do the real-time hybrid simulations. So this is the training side. We are training this neural network first, and then we also validated this neural network models by additional excitations. So here's some results on the comparing the hybrid simulations and the OpenSys numerical simulations, which means what I'm talking about the hybrid simulations here is only the hydraulic off mode, which is there's no restoring force feedback from the to the analytical substructures. You can see after we training the neural network soil models, the OpenSys results, our model results match very well with the OpenSys results. The next, what we gotta do, we started doing real-time hybrid simulations on this 2D structure models equipped with nonlinear viscous dampers. So for the OpenSys model, we are adding 6 numerical viscous dampers on the outrigger columns. And for the hybrid simulations, one of the viscous damper was physically modeled in the lab. And here's some results. So first, we did the training on the neural network, and then we also validated this to minimize the error. And you see what the hybrid simulation result match very well with the OpenSys results. So the reasons because we are adding a physical nonlinear viscous damper, but because our excitation is wind hazards, basically the structure behavior is linearly. So then the viscous damper in the physical will not have that much different as numerical damping models. And here are some different wind hazards of damper deformations, which is the viscous damper we physically model in the lab. You can so for the along wind is the we reduced the wind speed to give a reasonable range because the damper have a physical limit. And you can see there's some like permanent damper deformations even under the wind because the nonlinearities of the soil. This is also highlighting the importance why we want to start to model the soil, consider soil structural interactions. So here's our 4-phase project. So the phase 1 and 2 is we're using the 2D structure models and also the neural network for the soil and the wind and earthquake hazards. And the 3 and 4 phase is we are extend our numerical model to 3D. Thank you very much.
Thank you, Liang.
Yeah.
Great presentation. I see some questions in the chat. Would you like to take that?
Yeah, there's a lot of questions.
No,
Yeah,
Dr. Lee, would you like to say your question?
Yeah, that was a quick question. So I just wondering what data was used to train the soil neural network model. Was
Liam,
it
do you want me to answer the
simulation?
questions? Sorry,
Yeah.
I didn't mean to interrupt.
Sure, Jim, you can answer.
This is Jim, sorry. So on the neural network, first, I don't want to say too much because it's a student's dissertation that they're developing, but the data that was used to generate was generated numerically using a full finite element model. So you're putting some faith into the fact that the numerical model, in this case, a full finite element model with the constitutive routine, which is Drucker-Proctor, could model things appropriately. Otherwise, if you don't have that information, you'd have to get experimental data, but having enough data sets may be difficult to obtain.
Sure. Yeah. Right. Thank you for clarification. Thank you.
Yeah, and what's also important, it's a good question. When you train a neural network, you don't want to overtrain, you don't want to undertrain.
Sure.
But
yeah.
as you train a network, you'll go through and replay the simulation, comparing the simulation that you trained with for each data set with the output. But at the same time, you do an independent one, which is a validation set, and from that you can monitor the RMS error, which should reduce. But again, you have to be very careful not to overtrain the network, because if you do, it's not going to learn, it's going to remember. And when you go to a brand new condition, different situation frequencies, it's going to give you an awful answer.
Okay, yeah, thank you for the answer.
Thank you. There was another question about the link for this dissertation. If possible, maybe Lehigh can share it on the chat box.
Yeah, I think, I'm sorry, Mal, sorry. I didn't mean to interject either. And you did a really good job, but I think the question may be difficult to answer without much background. So Xiaofuan is in the process of writing his dissertation, so you're not going to see it in print probably for, I don't know, maybe within a year. He's in the process of completing some of his experiments, from which he'll write some papers, and then, of course, his dissertation. So I would say the best thing to do in this case is to just keep an eye out for when these things are published. I think the dissertation itself, as I said, is about a year.